In this video, we shall look at the integration of another type of rational functions with quadratic denominator. As you can see, the numerator consists of a linear function, px plus q. So how shall we integrate this? So this type of integral is always reduced to two simpler integrals by the following substitution. So the substitution is the following. Let's assume px plus q is expressed in the following form. Constant a times 2ax plus b plus capital B. Now what is this 2ax plus b? It is simply the differential of the denominator. The capital A and capital B can be readily found as follows. To find capital A, let's compare the terms with x. So the coefficients of these x terms, by equating them left and right, you get p equals to 2 little a capital A. And solving for capital A, you get little p over 2a. So this is capital A. Next, comparing the constant terms, q to capital A times b plus capital B, we can write little q equals capital A times little b plus capital B. And you can solve for capital B as q minus capital A little b. And since we have already found capital A, that is p over 2e, and then times little b. So this is capital B. So substituting a here and capital B there, we get the following. And substituting this line in here, we can break the original integral, say the original integral is I, into two integrals. This and that. Now let's call the first integral I1, so you can write the first term as quite simply I1. And let's call the second integral I2. So pb over 2 little a I2. I1 is straightforward. Setting the denominator of I1 as u. So u is ax squared plus bx plus c. So that means the differential du is 2ax plus b dx, which is what appears there. So that means that I1 integral can be rewritten as follows. Du over u, let's not forget the coefficient p over 2a. So this is an easy integral to do. That's going to give you a natural logarithm. That is natural logarithm of u. So together you're going to get p over 2a, substituting the original u. U is the denominator of that integral. You get natural log ax squared plus bx plus c. So that is the answer, the result of this entire first integral. Integration of the second part, I2, has already been explained in our previous video of integration of rational functions. Namely, there we mentioned that three solutions are possible depending on which of the following three cases an integral corresponds to. So case 1 is when a is positive and 4ac minus b squared is also positive. And then you have case 2 where a is positive but 4ac minus b squared is negative. And case 3 is where a is negative and 4ac minus b squared is also negative. So I urge the viewers to refer to that video to get a detailed explanation of how to handle this integral. As an exercise, let's look at the following integral. Now, the first thing is to rewrite the numerator 8x plus 7 as a constant a times the differential of the numerator, which is 4x plus 5 plus a constant capital B. So by comparing the left-hand side and the right-hand side, we can determine the coefficients capital A and capital B. And that will turn out to be A is 2 and capital B turns out to be minus 3 if you do the algebra. Now substituting this inside here and putting this result inside the integral, we get the following two integrals. Now the first integral is pretty straightforward. As we explained before, if you let the denominator of the first integral, of the integrand of the first integral, to be the variable u, then you simply get du equals 4x plus 5 dx, which is exactly that what is appearing there. And that's going to give you an integral of du over u, integration of which will give you a natural log of u, which now we know, since we have set u to be this function, we can just substitute that and you have that. So the first integral is done. Now let's look at the second integral. Which of the three cases does this integral belongs to? So in this integrand, a is 2, b is 5, and c is 9. So that means a is positive, 4ac minus b squared is 47, which is also positive. So that means you have case 1 here. If you recall, case 1 means the solution will be in the form of arctangent. So let's just look at this integral. Let's try to complete the squares we did before. Now this will become, when you complete the square, it will be 1 over 2. You can take the 2 out. X plus 5 over 4 squared plus 47 over 16. So that's what this integral becomes after completing the square. Of course, another thing just to realize is that the second term can simply be written as square root 47 over 4 squared. So note that this integral is exactly in the form like this: beta squared plus alpha squared, where alpha is the subject of the integration. And for this integral, the solution is obviously 1 over beta arctangent alpha over beta. So in this example, your alpha is this entire thing here, x plus 5 over 4, and your beta is square root 47 over 4. So let's apply that to this integral to get the solution. So now writing the complete solution, do not forget the 3 and the half. So the final solution for the second part is 3 over 2, 1 over the constant, which is a 4 over square root 47, that is like the 1 over beta in our previous formula, arctangent alpha, alpha here is x plus 5 over 4 over square root 47 over 4. So remember, this is a solution to the second part of the integral. So there will be some simplification here. So that's going to give you a 2. And let's write the complete solution side by side with the first solution. So 3 times 2, that is 6 over square root 47. I'm simply writing this line on top. Arctangent x plus 5 over 4 over square root 47 over 4. So that is that term right there. If you multiply the terms in the bracket up by 4 and down by 4, essentially multiplying the entire thing by 1, it doesn't change anything. You can rewrite the solution more neatly. So it's going to be 6 over square root 47 arctangent. So the numerator will become 4 times x is 4x plus a 5, because the 4 will cancel the 4 here, over square root 47, because this 4 will cancel that 4. And there you go, you have the solution for the second integral. And finally, you arrive at the complete solution, complete result to the following integral. And that solves the problem. Thanks for watching.